السلام عليكم ورحمة الله وبركاته. أهلا بكم أبنائي وبناتي طلاب الصف الثاني الثانوي مع حلقة الكيمستري. نرحب بكم منصة البث المباشر وزارة التربية والتعليم جمهورية مصر العربية. معكم مستر حسام حسن. We start now in the ionic bonds. In the last session we started about the types of bonds. Type of bonds classified into many things. I explained before the difference between types of bonds. We have two types of bonds, physical bonds and chemical bonds. Physical bonds classified into hydrogen bonds, and physical bonds classified into two types, metallic bonds and hydrogen bonds. And we have the chemical bonds classified into three types, ionic bond, covalent bonds, and coordinate bonds. I illustrated before when I finished the last session in ionic bonds. Now we review the ionic bond. We have the ionic bond is a type of chemical bond that arises between two atoms when electrons move from one atom to another. First one, metals, and the other is non-metal. Metals tends to lose this electron, and non-metals tends to gain this electron. We have the reasons for that. Which reasons for that? Metals have very low ionization potential, and non-metals very high electronegativity. So it is tendency for it to gain the electrons when it reacts with the metal. And metals, it had the ionization potential is very low. It tends to lose electrons and convert it into positive ion. Non-metals converts into negative ion. So they attract to each other and form the ionic bond. Now, this transition leads to the formation of ions and atoms that lose. I illustrated this before, and the other is gain. Now we have in this example Na converts into A positive and attracted to the chlorine ion. Now we can see the anion and the cations attracted to each other. Sodium ion with chloride ion. This sodium atom begins to lose its electrons when it gains thermal energy and turns into a positive ion. It's called the cation. As well as the chlorine atoms gain these electrons and release energy from this equation. Now then electrostatic attraction occurs between the positive sodium ion and the negative chloride ions, forming sodium chloride bonds. Now we repeated that the attraction here, sodium and fluorine ion. Sodium lose one electron and fluorine gain one electron, and forming ionic bonds here. And the attractions between the two ions here are illustrated in this figure. Now we converted to the others to form an ionic bonds. This ionic bonds following conditions must be met. Big difference must be, first one, big difference in electronegativity. There must be a big difference in electronegativity, like equal to more than 1.7. Typically, it must be typically one atom has a high electronegativity, such as oxygen or fluorine, chlorine, and any non-metal. And other how a low electronegativity, such as sodium, has a low electronegativity, low ionization potential. It is very easy to lose this electron. When lose this electron, convert it into positive. So the difference in electronegativity 1.7 and more. So low ionization energy and stable of informations. This is formations for I illustrated that before. Now we will next here in this example we show that in this table. We have NaCl, MgCl2, AlCl3. Now, I illustrated this before in the last session. Now, we will transfer into the session covalent bond. What is the nature of covalent bond? And the we know the behavior of any atoms at gain, lose, or share of electrons. Now we must know before what the meaning of covalent bonds. Covalent bonds formed between atoms with an electronegativity difference of less than 1.7. I showed that before because the difference between two atoms must be less than 1.7, and this type of covalence bond called polar covalence bond. Polar covalence bond. Now it occurs due to the sharing of electrons between atoms. If we have hydrogen and oxygen as example, hydrogen is non-metal, oxygen is non-metal, they have no tendency to lose, but they have tendency to gain electrons. Which one gain from the other? No one. Hydrogen needs to gain. Oxygen needs to gain. Okay, we have a solvent. We have a moderate solvent. This solvent is each one share a number of electrons like the other. Oxygen share by electron with hydrogen, and hydrogen share by one electron too. Now it occurs this between two hydrogen atom and one oxygen atoms, between the three atoms. This where each atom share the same number of electrons as the other atoms. We have this example. We find fluorine and fluoride. Firstly, you must basically do electronic configuration of fluorine 2, 7, 2, 7. Each one share by one electron. This is a sharing bonds between them. This is a covalent bond in this here. Share one and one. One of fluorine and one the other of the other fluorine. This is the covalent bond. This is a valence electrons. We have before, according to Dots model or Lewis model dots, we have dots of electrons. As we observe, each fluorine atom share one electrons only from the valence electron in the sphere. Now this electron and valence electron in the outermost energy level. Now we transfer the type of covalent bonds. We have three types of covalent bonds: polar covalent bonds, non-polar covalent bond, and pure covalent bond. The first is pure covalent bond. Polar covalent bond and non-polar covalent bond. What is the difference between these types of bonds? First, the pure covalent bond, the electronegativity difference equal to 0 between two atoms. Here in this example, non-polar covalent bond, the electronegativity difference is less than 0.4 and not equals to 0. Polar covalent bond, the electronegativity difference is less than 1.7 and more than 0.4. We have this condition to understand the types of the covalence bonds. We now transfer the other slides here and to know these elements, non-metals and non-metals, to form covalent bonds. Covalent bonds are often formed between non-metals elements. Which one? Non-metals. We have in this figure the section of periodic table, and this section is a non-metals atoms. These elements are concentrated on the right side of the periodic table as shown in this section. like nitrogen, oxygen, fluorine, chlorine, phosphorus, sulfur, and so on in this section in the right side of periodic table. Now, we must know what one this HCl is the covalent compound. HH is a covalent molecule element. H2O is a covalent molecule compound. ClCl, it is a covalent, pure covalent, or I call this chlorine Cl2. Cl2 is a covalent element. Now we have different types of covalent bonds. Here is polar, here is polar, here and pure. Now, covalence molecules, we find different examples for covalence bonds, some of which are compounds and some are elements. But we will later clarify examples for each types of covalence bond, and we transfer in the next slides to understand the nature of covalence bonds I illustrated before in this example. They are formed only between similar nonmetals. This is, I mean, pure covalent bond. Now, must be two identical atoms. Oxygen, oxygen, nitrogen, nitrogen, fluorine, fluorine, chlorine, the same. Chlorine Cl2, Cl and Cl. Fluorine F2, F and F, and so on in these types. We have fluorine molecule. This is a molecule, element molecule, FF. This is the chairing point, or this is a center of this bond. This nonmetals elements, the electronegativity difference electronegativity between them equal to 0. The atoms of elements, this valence electron share by one electron and the other share by one electrons. I have example bromine, Br2, fluorine, F2, hydrogen, H2, this oxygen, nitrogen, chlorine, they are examples for pure covalent bonds of the elements only. No pure covalent bond in compounds. Pure covalent bonds only n elements. Why? Because the difference between them equal to 0 in electronegativity. Second type is polar covalent bond. Polar covalent bond, the difference between them 1.7, less than 1.7. How does polar covalence bonds form? For example, we have HF. HF have one electron in outermost energy level, and fluorine equal to 7 electron in valence electron. Okay. For example, in this hydrogen fluoride molecule, electronegativity of fluorine is 3.98. Don't say that, but you must know it only. And hydrogen is 2.1. We find that the more electronegativity fluorine atoms attracts the electrons of the covalence bonds more towards. Focus on this word. I have fluorine and hydrogen. Fluorine equals 3.98. Hydrogen is 2.1. Now, if you make subtractions between 3.98 minus 2.1, okay, equal to 1.6 maybe 2.087. Okay, this is a polar covalent one. So, which one is greater than the other in electronegativity? Fluorine. Okay. Fluorine share by one electron only, and hydrogen share one electron another. So the fluorine have more electronegativity. It attracts the two electrons on the bonds towards its more than the other. It takes a more time. The time attraction for hydrogen is less than fluorine. So is polar is found here. We find that more electronegativity fluorine spend more time around the fluorine atoms. As a result, the fluorine atoms acquire small or partial negative, partial negative, not totally negative, but partial. What did I mean partial? Partial, I mean it spend a more time, negative, spend a more time in fluorine than hydrogen. So hydrogen carried a positive charged sign. Now, atom atom of fluorine have negative partial. Hydrogen have positive partial. As a result, this fluorine atom acquire a small or a partial negative charge, not a full negative charge. As the case of fluoride ions, this means while the hydrogen atoms, due to the slight displacements of electrons away from it, acquire a small or partial positive charge. Now hydrogen have positive charge partially, and fluorine have negative charge partially. Now I explained the difference between them in electronegativity. I repeated that here in H2O, hydrogen, oxygen. If you know, oxygen here attracts these electrons towards it a more time than hydrogen. So oxygen carried negative 2 partial sign. Hydrogen carried positive charged sign. Okay, why? Because the electronegativity of oxygen more than hydrogen. The type of covalent bond here is polar covalent bond. As shown, the electronegativity of the oxygen atom is greater than that hydrogen atom. So the electrons of bonds are more attracted to oxygen atoms than to hydrogen atoms. The bonding electrons spend more time in oxygen more than hydrogen. Now we know the difference between them less than 1.7. The type is polar covalent bond. We have this exercise. You arrange the following compounds in a descending order. In ACl, AlCl3, MgCl3, MgCl2, MgCl2, KCl according to electronic conductivity. Okay, we have an ACl, I illustrated before, is ionic compound. AlCl3, covalent compound. MgCl2, ionic compound. KCl is ionic compound. Okay, how can you know that? I have this table. This table have this number of electronegativity. Yes, you make subtracts El minus 3, Mg minus 3, Ka minus 3. If you make subtracts between El 1.5 minus 3 equal to 1.5, okay? Mg 1.2 minus 3 equal to 1. Register it please in your paper to make arrangement. 1.2 minus 3 equal to 1.8. This is less than. This more than AlCl3. Okay. KCl 1.3 minus 0.8 equal 2.2. This is the highest one of the difference of electronegativity. So KCl is the highest in conductivity of of electricity because it have the highest difference in electronegativity. NaCl, NaCl with NaCl, Na 0.9 minus 3, so equal to 2.1. So descending a KaCl, MgCl2, sorry, KCl, NaCl, MgCl2, Al3. This is a descending, not ascending order. Now, H2O, HF, NH3, H2 according to polarity, the same. You must know the HF is the most because the difference in electronegativity, which fluorine for hydrogen equal to 2.1. 4 minus 2.1 equal to 1.9. Okay, this is the highest. NH3, you make this the same subtractions. Now you make the subtractions between them and the electronegativity. You can ascending easily by using the mathematical way. Now KCl more than NaCl, HgCl2, AlCl3. HF more than H2O more than NH3 more than H2 because it is 0 equal to 0, hydrogen equal to 0. H2S, BH3, HF, BCl4 according to number of ions per number of lone pairs, lone pairs of electrons. This is needs to make electronic configuration of them. This is electronic configuration of them. Number of lone pairs of electron in H2S molecule, number of lone pairs in electron negativity in electrons in BH3. Sulfur 16. Now this is electronic configuration of it. Okay, and we have the phosphorus P15. We have 1, 2, 3, 4, 5, 6. This is electrons, BCl5. Okay. Now we have 1, 2, 3, 4, 5, 6, 7, 8. Count these number of electrons. This is a lone pair. But this is bond pairs. This is orange blue. Difference. Any difference here? Any difference electrons here? This observe the bond pair. This is a lone pair. Now number of lone pairs of electron in BCl5 equal to 15 lone pairs, 15 ion pairs, and we have bond pair 1, 2, 3, 4, 5 bond pair. Okay, now number of pairs of electron in HF, the same in HF 2, 1, 2, 3, 3. I have 3 and 1 F and 1 bond pairs. So we have 3 bond pairs? No, I have 3 lone pairs, but I have 1 bond pair. So the arrangement is BCl5 have 15 is his H2HF and H2S and BH3. This is the arrangement of it and according to number of lone pairs of electron in HF. I have another exercises that show the number of electrons. Draw BCl5 molecules by Lewis dots diagram. B equal to 15, Cl equal 17. How many lone pairs of electrons in urea? This is a urea. A, C, double O, N, H, H, N, H, H. Now we have P15, 10, 3s2, 3b3. 3s2, 3b3. We have 3 bond pairs. 3 bond pairs. Now is phosphorus 1, 2, 3. 1, 2, 3. This is a lone pair. Chlorine, lone pair, lone pair, lone pair. Now, imine has BCl5. This is a urea. Okay, focus. It is a urea. Carbon, this is a lone pair. This is a lone pair. No, it is bond pair, and this is bond pair, and this is bond pair, and this is bond pair, bond pair, bond pair, bond pair. But this is lone pair. This lone pair doesn't make any bonds with another atom. Oxygen make double bond, share by 2 electrons, and the other is 2 electrons. You make the different shapes here and these dots. This dots diagram of Lewis explains that. Now you can show that there's a difference between them. I have many theories observed and explain the octet rules. I want to know very important things. I want to explain it for you. What is the difference between ionic and covalent compounds? I will illustrate this quickly, but I will explain this in the next session, inshallah. Now we have ionic compounds. This is ionic compounds. High melting point, high boiling point. They are solids. Its solution and molten compounds are very good in conductivity of electricity. Covalent compound, low melting point, low boiling point. They have different cases like solid, liquid, gases. HCl is gases. Sugar is solid. I have many things, examples for covalent compounds. Conductivity of electricity, no, it is not good in conductivity electricity because it is a molecules, not ions, no free ions here. Okay, now transfer and the octet rule, electronic theory of valence. Koso and Luis illustrate this theory. We have many theories explain the meaning of and explain the shapes of covalent bonds. Our sharing of this covalent bonds explains by octet rules, chemical rules that reflects the observations that atoms, main groups elements tends to combine in such a way that each atom has 8 electrons in valence shell. Any atoms have 8 electrons in the outermost energy level. I call it noble gas or inert atom because it is very stable atom. This stable atom doesn't need to share, lose, or gain electrons but it is inert elements. So the octet rules depends on the theory. Any atom tends to reach octet structure. Why? Because this number is a stable number for the outermost energy level. If you use this BCl3, you must count the number of valence electrons around phosphorus when it makes 3 bonds between PCl, Cl, Cl. 1, 2, 3, 4, 5, 6, 7, 8. Yes, this molecule obey octet rules. This is a urea. Carbon 1, 2, 3, 4, 5, 1, 2, 3. Okay, this is 8. Nitrogen 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen here 1, 2, 3, 4, 5, 6, 7, 8. And here Oxygen 2, 3, 1, 2, 3, 4, and we have 4 this electron, and to form this bonds equal to 8. Thus the Coastal and Lewis theory applies to carbon dioxide molecule and is molecule considered polar. We have carbon 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is oxygen. And hydrogen 1, 2, 3, 4, 1, 2, 3, 4, 8. And oxygen here. So Coastal and Lewis theory obey this compound. This compound obey Coastal and Lewis. This Coastal and Lewis theory, which is based on the octet rules, applies to the carbon dioxide molecule. The carbon atoms form a double bond. This is a double bond here, and this is a double bond here, with each of 2 oxygen atoms, resulting in a stable configuration. The atoms has 8. So this obey for the octet rules. Electron in its valence shells, polar or non-polar. Here, this is compound is polar or non-polar. No, it is non-polar. Why? Electrons in its valence shells, polarity of carbon dioxide, despite the polar covalent bonds between carbon and oxygen. The carbon dioxide molecule is non-polar. I told that before. Non-polar overall. Why? This is because the molecules has a linear shape. This is a linear shape. And the die moments, moments here, polar and polar, they are cancelled each other. So the double moment in carbon O and carbon O, each of them is cancelled this moment. These moments, the 2 moments, cancel each other out, resulting is no net dipole moment. No dipole moment. Okay, this is octet rules. Okay, I want to do the drawbacks of octet rules, disadvantage and advantage of it. I have disadvantage of octet rules. Which one? You show this molecule. Okay, you must count this number. Phosphorus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 electrons around phosphorus. Doesn't obey of octet rules. Okay, P 1, 2, 3, 4, 5, 6. Doesn't obey. No 8. Here more than 8. Here is less than 8. So we notice that the phosphorus molecule is surrounded by 10 electrons around the central atom, which exceed the number of 8. It exceeds this more than the number of 8. And here octet rule is not satisfied for the molecule electronic defense molecule. So we can repeat this as P center atom. Here we have less than the 8. So they are satisfied into octet rules. Now, this exercise, we find ionic compounds. We finished that by this exercise using the following: A 15, B 11, C equal 9, D 6. Ionic bond is B 11, and polar covalent bond compound C 9, and this nonpolar covalent compounds D6 and A15. And we have AH3. It is a covalent compound whose molecules containing 3 bonds pairs and 1 lone pairs is AH3. Covalent compounds here is HC. Now covalent compounds here is DH4. Now we finished our session now, and I am very happy to finish my session, and I will hope to understand my sessions today, and the meeting is over, and we'll see you later. Hopefully I meet you next week, inshallah, for the new session. Bye bye. والسلام عليكم ورحمة الله وبركاته.